this computer. All right, we'll be recording our third acoustics session, and we're going to finish off the topic on frequency, wavelength, speed of sound, and stuff like that. I think I said last week that the purpose of today or this week was we were going to just do a quick review of where we came through and then crash through the bitter end that we hadn't finished. Okay, and that would be the idea here. So if I share screen and pull up the particular notes in question here, you will see what we did. And I'll pull up the particular PowerPoint we had in mind. I'll pull that copy up as well. Okay, here we go. Okay. So, hey, how are we doing, Ramirez? Okay, we got 4 of us all together. This is great. Okay, so we are looking at the very fact of sound waves being molecules moving in the air, condensed, rarefacted, condensed, rarefacted. And we also said that when we draw condensed, rarefacted, we draw the wave up is the condensed, down is the rarefacted. We said sound waves don't actually go up and down like that. That's water waves. And and sound waves are really squeezing and separating of molecules. The next division in our notes concerned this: sound waves, longitudinal versus transverse. And we said transverse water waves are like water waves. They go up and down, and the direction goes this way. So the up and down movement of the wave is perpendicular to the direction of the wave. The wave may be moving towards shore, but the wave action is going up and down. Transverse. Sound waves, we said, are longitudinal. They don't go up and down. They're squeezing, separating is parallel to the direction in which they move. We draw sound waves like up and down because it's easier than drawing this. Okay, slain and pimple, plain and simple. Okay, then I said the bottom third of page 1, don't freak too much about this at all. This is mainly for nerds. Okay? It's not a bad thing. You're welcome to read it, but it's basically talking about this. I will show you. Going in here. Remember we said a circle is 360 degrees? Mm-hmm. Remember we said a sound wave is like a circle, but that's broken in half and bent outward? So you still have 360 degrees? Okay, 0, 90, 180, 270, 360. Now you're back to where you started from. Well, if you turned this bottom half and turned it to go over here, it wouldn't be a perfectly round circle, would it? It would be some weird oblong thing like this, kind of. That's all that the bottom piece is talking about here. That's all it's talking about. Okay? It's talking about this fact. See how the black area isn't all thoroughly black all the way across? It's grayish, and then gets black, and then gets grayish. And the white isn't totally white. It fades in and out. That's all that stuff is talking about, okay? Other than that, don't worry about it. For nerds and nerds alone. Okay, next. Then we said that there are 2 ways to represent sound. And this is important, but we will come back to this in a couple of weeks. So I'm mentioning it here, but we'll come back to it in a couple of weeks. One way to represent sound is as a wave. Okay, sound waves. And when you're looking at sound waves, and you saw this picture too, okay, the 2 axes of a sound wave. The horizontal axis is time. The vertical axis is amplitude. Just like this. Well, not that one. Here. Time, amplitude. Okay? That's the axes around a sound wave. That's the length here. This is called time, and this is amplitude. A second way to represent sound is like this. A spectrum. And notice the horizontal axis no longer reads time. It reads frequency. Maybe you were talking about like a trumpet. Okay, and you're talking about the sound coming from a trumpet or some music or traffic or whatever. What a spectrum is, this is a spectrum. Horizontal axis is frequency, vertical axis is amplitude, and a spectrum doesn't have time. There's no time on it. You see, sound has 3 dimensions: frequency, amplitude, time. But a piece of paper has only 2 dimensions: width and length. So if you're going to draw sound on a 2-dimensional piece of paper, you're going to need 2 kinds of pictures to show all 3 dimensions. Because a sound wave just shows amplitude and time, and a spectrum shows frequency. Okay? Time is spoiled because it's on the vertical axis in both a sound wave and a spectrum. So time is spoiled, or amplitude is a spoiled little kid. Okay? Anyway, think of a spectrum as a slice. If you think of the sound wave as a loaf of bread, a spectrum is a slice of that bread. I'll stop sharing. A spectrum is a slice of that loaf of bread turned sideways so you can see the raisins. Okay? So a spectrum is excellent at showing you what frequencies are in a sound. A sound wave, it's hard to tell what frequencies are in the sound. You'll have to figure out the length, the period of the sound wave, and you got to do the math and calculate what frequency that must have been. The spectrum just goes, oh, these frequencies are in the sound. Done. A sound wave, though, is better for showing you what happens to that sound over time, as it got louder and softer over time. So they each have their advantages and disadvantages. Here's what I will tell you in our field. We are learning about sound waves mostly right now, today and last week and the week before. But in the future, going forward, we will be more talking about spectrums, because hearing aid specs, what hearing aids do, the specs of a hearing aid always show you the spectrum. They don't talk about the sound waves. But it's important here that we learn what sound waves are, because we're just beginning to learn what the heck sound is. So we got to start someplace, and that's why we're talking about sound waves at first. Okay, back to your notes. So that's what that grayed out area was. Then we talked about amplitude, frequency, and time, or sound taking place over those 3 dimensions that we just talked about. And the best slide to look at that is over here. I'll go up to this one right here. This is a great, I like this slide. Okay, and this slide shows you very plainly the 3 dimensions of sound. Here's 2 tones of a different amplitude on the top. They have the same frequency, the same number of bumps per second. So pretend this is 1 second from here to here. These are sound waves, so the horizontal axis is time. So 1 second, 1 second, 1 second. So how do these top 2 tones differ? They differ in amplitude. The wavelengths are the same. The time it takes to complete each cycle is the same. Look at this, from here to here. From here to here. 0 degrees, 90 degrees, 180, 270, back to 360. 0 degrees, 90, 180, 270, 360. 0, and so on. The same amount of bumps here, the same amount of bumps here. The frequency would be identical. They differ in height, amplitude. The middle pair, now we're talking about the next dimension of sound, frequency. The time is the same for both, but look, this has a longer wavelength than this one. To go from 0 to 90 to 180 to 270 to 360, longer time than here to get to where you were again. So these 2 are the same height. The peak to peak is the same in height. So they're the same amplitude. They just differ in frequency. This would be the lower pitch tone. This would be the higher pitch tone. The next pair are the same in amplitude, the same in frequency, but they differ in phase. When this one's condensed, this one's rarefacted. When this one's rarefacted, this one's condensed. So if these two were played at the same time, they'd cancel each other out. So they differ in terms of phase. All right, so now we stop share. Okay, I'm going to just say, let's go to our good old notes. So that's now we work our way down to frequency and period. This is just reviewing. We're just playing here, but it's all good because we're going to finish this whole section today and be done with it. Thank God. No. Okay, so frequency and period. And I said last time, when you hear the word period, think your watch, time. What is the time it takes for one cycle to occur? Read what it says. Frequency, the number of times something happens per unit of time. Let's call in sound, the unit is a second. It's always not a minute, not an hour, it's always a second. How many something per second? You can count the frequency of your footsteps per second. How many footsteps are you making per second? Are you running or are you walking? What's the frequency of your footsteps? Okay. In sound, we talk about what's the frequency of the cycles. How many cycles took place per second? And we call that hertz. H-E-R-T-Z. You know, when I taught this very same class yesterday to a Canadian college, I said hertz, capital H, small z. They call the last letter of the alphabet Z. You in the States call it Z. Just thought I'd tell you. You guys also spell the word color differently than we do here. You spell it C-O-L-O-R. We spell it C-O-L-O-U-R. Neighbor, O-U-R. Harbor, O-U-R. That's the British. Oh, quite. The Queen, Queen Elizabeth, eh? Yeah, quite. I'll have a sip of tea. I'll show you something here. I'll stop sharing. This is a picture. This glass, this cup, is a picture of the very first group of HIS students I ever taught. Class of, I think it's 2000 and what was it? Class of 2007. They call themselves survivors. I just thought I'd show you. You got to break it from acoustics once in a while. All right, here we go. Now we will go back to good old share screen. We're talking frequency and period. Frequency, the number of times something happens per unit of time. For sound, frequency refers to the number of cycles per second. Hertz. 1 hertz means 1 cycle per second. A sound with a frequency of 100 cycles is 100 hertz. Period is the time it takes to complete 1 cycle. So if a sound is 1 hertz, then its period is 1 second. But if a sound is 100 hertz, then its period is 1/100th of a second, because 100 of them took place in a second. So that means frequency and period are inversely related. As frequency increases, period decreases. So frequency is 1 over the period, period is 1 over the frequency. So if you think of it, let's try this with 500 hertz. What's the frequency of 500 hertz? Or I should say the period of 500 hertz. Period is 1 over the frequency. Period equals 1 divided by frequency, 1 divided by 500, and you'll get 0.002 seconds. I think Renee had this last time, okay? And you'll get 0.002 seconds, or 2 milliseconds. Or in French, 2 millisecondes. We have a lot of Français in Canada, oui? Anyway, I can't speak French very well. Anyway, so period is 1 over frequency. Frequency is 1 over the period. So if I said to you, what's the frequency of a sound wave that has a period of 0.002 seconds? You'd do 1 divided by 0.002 and you'd get 500. 1 divided by 500 is 0.002. It's a frown is an upside down smile. A smile is an upside down frown. There you go. And then we talked about the range that we can hear. The range that humans can hear. And this brings it more to clinic. We can hear from 20 cycles per second, which is very, very low, to 20,000 cycles per second. But that's only when you're 10 years old. By the time you're 20, you can't hear 20,000 anymore. By the time you're 30, you can't hear 18,000 anymore. And so on and so on and so on. The frequencies we test in hearing that you will be doing in your clinics, that you will be practicing in your audiometry course, that you will be taking soon. Are you, any of you taking audiometry right now? Are you taking audiometry? Not yet. Good. Yeah. I'm always saying, because I always think people should start out taking acoustics and taking anatomy, and take these two courses, and they build on top of them audiometry and hearing aids. Last semester, we had students taking 110, 120, which is acoustics and anatomy, and 130, hearing testing, audiometry, and 140, hearing aids. And I'm thinking, too much. Anyway, it's too much. So when you're thinking about the range that we test in a hearing test, we test from 125 hertz, which is low C on a piano. The next octave, you double the frequency, 250 hertz, middle C. The next octave higher, double 250 is 500 hertz. That's basically low C, middle C, and high C in music. Now you're leaving music range. Now we test at 1,000 hertz, and then at 2,000 hertz, 4 and 8. Here, 8. So 125, 250, 500, 1,000, 2, 4, and 8. 7 octave frequencies. Beyond 8,000 hertz, speech doesn't exist anyway, so nobody cares beyond 8,000 hertz. But by the time you hit 65, you're losing 8,000, you're losing 6, you're losing 4, and so most people have a sloping, high-pitched hearing loss. At any rate, share screen again, look at the notes, here we go. All right, now we get into the next section of the notes, and the next section of the notes was talking about the speed of sound and actually the physical length of the wave. So the focus here now is no longer on the period. That's time. We'll leave that one alone now. We'll talk about the physical length of sound waves. How long are they in feet or inches or what have you? And the length, the physical length of a sound wave depends on the speed of sound. And as we said last week, the speed of sound in air is 340 meters per second. To be exact, 343, but we don't care. 340 is fine, okay? The speed of sound in air is also 1,130 feet per second. Doesn't matter, whichever one you want to use, doesn't matter. Feet, seconds, Polish, German, Protestant, Catholic, we're all good, okay? Here's the point. The speed of the wavelength over 1 is equal to the speed of sound divided by the frequency. So here's your here's the way you can look at it. Wavelength is speed of sound over frequency. Frequency is speed of sound over wavelength. Speed of sound is frequency times wavelength. Whichever you want to figure it, they all work together. Just like 5 is equal to 10 over 2, or else you can say 2 is equal to 10 over 5, right? Same thing. Or 10 is equal to 2 times 5. It doesn't matter. You can just flip these things around. It's just simple arithmetic. But for wavelength, wavelength is speed of sound over frequency. And whenever you're doing these things, always just say wavelength over 1 is equal to speed of sound over frequency. So for 100 hertz, 340 or 343 meters per second, close enough for government work, doesn't matter. The wavelength is going to be 3.43 meters. Want to do it in feet? Wavelength over 1 is equal to 1,130 feet per second divided by 100. The wavelength is 11.3 feet. 11.3 feet is the same as 3.43 meters. Same length, just different language. For 250 hertz, 343 meters per second divided by 250 is 1 0.3 meters. Or 1,130 feet per second divided by 250 is 4.5 feet. Now this kind of ties into anatomy a little bit. Think about it. Well, I'll show you, but let's do 8,000. For 8,000 hertz, 340 meters per second divided by 8,000, that's 0.04 meters. Do you know how long that is? Now, for those of you who know anything about metric, a meter is about a yard, 39 inches. 0.04 meters is 4/100ths of a meter. So a meter has exactly 100 centimeters. Cent, C-E-N-T, is the French word for 100. M-I-L-L, mille, is the French word for 1,000. Okay, how many cents are in a dollar? 100. Now, so when you think of 4 centimeters, a centimeter is the width of your fingernail. So you put 4 of those puppies together and you'll end up with something about yay big. So an 8,000 hertz tone is about a little more than an inch and a half long for one cycle. Let's find out the wavelength of a 1 hertz tone. 1 cycle per second. Go back to share screen. Let's try that. What would putting that into the formula? What's the wavelength of a 1 hertz tone? Check that out. Well, wavelength over 1 is equal to 340 divided by 1. What's 340 divided by 1? 340. 340 meters long? Yep. A 1 hertz tone is over 340 yards in length. That's long. Okay? Do it in feet. Wavelength over 1 is equal to 1,130 feet per second divided by 1. What's that? 1,130 feet. 1,130 feet! That's like a quarter mile. Yep. That's how long a frickin' sound wave is of 1 hertz. Get it? Got it? Good. It should tell you this. When you look at the bottom of the page, look at these 3 lines here. Lows have long sound waves. Like, real long. Elephants emit low-pitched tones. We can't hear them. They bend around valleys and hills. They are that long. Okay? That's why ships use low-pitched foghorns. Because lows can bend around islands and other boats can tell that there's a boat around there. Okay? But lows bend. Highs bounce. Little short waves aren't long enough to bend around things. They're too short. They bounce. And we said last week, bats use high-pitched squeaks that we can't even hear that bounce off of bugs. They use it like radar. So, and high pitches leak out of hearing aids. They bounce. The sound hits the eardrum, leaks out from between the ear and the hearing aid, gets picked up by the mic, gets amplified, hits the eardrum, bounces back, and so you get that loop, a feedback loop. So that's caused by high-pitched sounds in a hearing aid. Next. The speed of sound, we'll just talk a little bit about that. The speed of sound, basically, in water, memorize this, it's 4 times the length, 4 times the speed in air. The speed of sound in steel is 14 times that of air. And we said last week, that's where you get the saying, I'll keep my ear to the ground. Okay, because sound goes faster through solids, slower through liquids, and slower yet through gases. Okay, now here's a trick in figuring some of this out. We also talked about the speed of light last week, so I won't do that anymore because we're not studying optics, we're studying hearing. So, but this is interesting. The speed of sound is influenced by the density and elasticity. Now, when you see that word density, think mass, weight, the heaviness, how tightly clustered things are together, the molecules. And when you think elasticity, don't think of rubber bands so much. Think of stiffness. All objects have mass and stiffness. And these two properties are going to be playing a huge part in what we study in sound, even in the ear. Okay, everything, mass and stiffness. Low frequencies resonate mass. When you're sitting in your apartment and the people upstairs are playing loud music, what comes through your ceiling? The bass guitar and the drums, because your ceiling has mass. Boom, 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 boom. Okay? You can't jiggle a locomotive. You can't take a train locomotive and go, yeah, 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 yeah. Okay? You'd have to have 100 people pushing the locomotive and then 100 people pulling the locomotive to make it move back and forth. Mass doesn't like being moved back and forth. It hates it. Okay? Stiffness, it's the opposite. If I have a stiff spring sticking out of the wall, it's hard to push in and hard to push out. But if I brace my legs and go, yeah, 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 no problem. Stiffness likes high frequencies. Mass likes low frequencies. So low frequencies resonate mass, and high frequencies resonate stiffness. And your ear has a shape like this because these bumps and the ear canal being 1 inch long or 2.5 centimeters long, the mass and stiffness of that ear likes or resonates with high pitch. And what are high pitches in speech? Consonants. So your outer ear has the shape it does to emphasize high frequency consonants. It's all mass and stiffness, mass and stiffness. And your outer ear, we said, is also a quarter wave resonator. It's like a cup closed at one end and open at the other end. And quarter wave resonators vibrate with sounds 4 times their length. We did that last week. So at any rate, back to good old share screen here. Taking a look at speed of sound depends on the density, the mass, and the stiffness. Now we're not talking resonance here, we're talking speed of sound, okay? And don't worry about inversely related to square root of density, blah, 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 whatever. Who cares? Don't worry about this so much either. All this means is sound travels faster through hot air than through cold air, but hardly any difference, just a smidge. The difference isn't much. But here's something. We say, and you're going to get this on a test or quiz, so I would put a star by this section right here, okay? The more dense something is, the slower the sound goes through it. The more stiff the medium is, the quicker sound goes through it. So the more dense the medium is, air, water, steel, okay, the slower sound goes through. The more stiff the medium is, the faster sound goes through. And this should raise a question to you. You should be saying, well, that's weird, Ted, because the molecules in steel are way more dense than the molecules in air, so why wouldn't sound go slower through steel? And I'd say, yeah, but look at the stiffness side. Steel is also way more stiff than air. And the stiffness of steel outweighs its greater density. Look, steel is 6,000 times more dense than air, but steel is 1,230,000 times greater than air. The stiffness of steel is 1,230,000 times greater than that of air. Whereas so the density is outweighed by it. That's kind of for nerds. It's a bit of a twist. That's as difficult as it gets. Okay, here we go. Recall, wavelength, speed of sound, and frequency are all interrelated. Okay? They're all interrelated. Wavelength, speed of sound, and frequency. Those 3 things are all connected. The speed of sound here, I ask this question every year, and every year students get some mistakes on it. I don't know why. But in air, all frequencies travel the same speed. In water, all frequencies travel the same speed. Faster, but they all travel the same. In steel, All frequencies, bass, mid, and treble, lows, mids, and highs, all frequencies travel exactly the same speed, faster than they do in air, but by gum, they all travel the same speed. So when, not if, but when I ask this as a true-false question, please answer this one correctly. Because for some reason, can you imagine what an acid trip it would be if frequencies traveled different speeds in air? I mean, you'd be like lows and highs traveling different speeds. My voice would sound, quite weird. I think I'd be having a seizure. Anyway, all right, here we go. We got to get through this stuff here. Doppler effect. Did we cover the Doppler effect last time? Did we? I can't remember. Tell me.
A little bit, yeah.
Little bit. Doppler effect is simply this. It happens below the speed of sound. It's quite simple, really. It means if a car is coming toward you, you hear a higher pitch. And think of, I'll stop sharing so I can just, speed travels 1,130 feet per second, or 340 meters per second. Say that you're standing at a street corner and a car is coming toward you. So its sound is coming at 340 meters per second to you, or 1,130 feet per second, but also the car itself is coming toward you. So now you've got the speed of sound plus the speed of the car. Well, guess what? Those waves are going to bunch up. They're going to get squeezed. And because they're getting squeezed, you're standing still, so you're hearing the sound. The waves are getting squeezed, so the pitch goes up because the wavelength is shorter. So the car is higher in pitch, and as soon as it passes you, goes lower in pitch. Why? Because the sound is traveling toward you at the constant speed, but the car is moving away from you. So you've got the speed of sound minus the speed of the car when it goes away from you. So the wavelengths get longer. You remember, you're not moving, you're standing still. So you're the reference point. So when the sound is coming toward you, you got the speed of sound plus the speed of the car. So the waves are getting squished. You go away from you, now you've got the speed of sound, but minus the speed of the car. So the waves actually get longer. The pitch goes down. When you talk about let's say breaking the sound barrier, now you're talking about what happens if you go faster than the speed of sound itself. And don't memorize this, I'll just describe it to you. Here's a jet moving, and finally it gets to be 1,130 feet per second. That's 766 miles an hour. As soon as you start approaching that speed, your wavelengths are, remember, sound travels at its constant speed, but now the plane is equaling the speed of sound. So the speed of sound isn't ahead of the jet anymore. The speed of sound is at the jet. So all the waves, the noise from the jet, all the sound waves are right on top of each other. They're totally on top of each other. There's no separation. So all the waves are squeezed so tight that now you've got one massive condensation of molecules, one huge, massive condensation. And as soon as the jet gets through that whole big clump fills in the big vacuum of rarefacted molecules behind it. And that's the sound barrier, sonic boom. And I told you last week, a smaller example is going into the locker room and taking your towel and going up to your friend and going, snap! And the of the towel, the tip of your towel is breaking the sound barrier. That's why it too snaps. It's a little tiny version of a sonic boom. That's why the snap of a towel leaves a welt on your thigh. It hurts. Okay, it's going 766 miles an hour. That's gotta hurt. All right, enough on that. Now let's move on down to what we haven't covered much yet. We did cover a little bit about echo and reverberation, didn't we, last week? Mm-hmm. Okay, so we don't need to go so much into that. What we do need to get into is the stuff that we got to talk about here. Resonance. There we go. Resonance. Any object has a favorite vibrating frequency. This is its resonant frequency. This cup will resonate with certain sounds. A wine glass at Christmas. A pop bottle when blowing over it. Okay, will resonate. And when you've got resonance, you get an increase of intensity. Vibrations in any object are determined by its mass and stiffness. Where the heck have you heard that before? It's the mass and stiffness. Mass is the amount, the density. Stiffness is the ability to resist being bent. It's the opposite of compliance. As mass increases, resonant frequency decreases. For example, thicker strings on a guitar are the low-pitched ones. They have more mass. The thin strings on a guitar are high-pitched because they have less mass. As stiffness increases, resonant frequency increases. So hold your arm out straight, and I'll do this here. I'll stop sharing. I'll hold my finger out straight, really stiff. It's hard for me to push up, and it's hard for me to push down if I do it slowly. But if I hold my finger really straight and go, no problem. Okay? Stiffness resonates with high frequencies. Mass resonates with low frequencies. Put a star by that one. So now we get to something called your ear. And I think we covered this. Were all of you in the anatomy class 120 last week? Were all of you in that? Okay. Here's what we taught. Did you all listen to the Zoom session? Okay. When you did, we talked a little bit about this, didn't we? About the outer ear. Mm-hmm. Your outer ear is a quarter wave resonator. And let's see if we've got a picture of it in our PowerPoints here. Let's see, I may or may not sure if I do. I don't think I do in this one. I do in anatomy, but I won't worry about it right here. Let's just talk. Your outer ear is like a cylinder. Your ear canal is closed at one end, open at the other end. Okay, just like a cup. It's closed at one end, open at the other end. Of course, last week I spilled my coffee doing that one on the keyboard. So not going to do that again. Put some Baileys in that coffee. All right, here we go. So quarter wave resonators are cylinders. Cylinders that are closed at one end and open at the other end, read a cup, okay? They vibrate with sound waves 4 times their length. So if your ear canal is 1 inch long, it's going to resonate with sound waves that are 4 inches long. If your ear canal is 2.5 centimeters, which is an inch, if your ear canal in centimeters, if your ear canal is 2.5 centimeters, it's going to resonate with sound waves that are 10 centimeters, because 4 times 2.5 is 10. Okay, so always remember that. Quarter wave resonators resonate with frequencies 4 times their length. They're influenced by their mass and stiffness, but also they have this peculiar property being quarter wave resonators. Put a star by that, because that sucker's is always on midterms and exams. Always, always, always. It's important because you're going to learn this when you learned in anatomy class. Let's just do the math. You've got, remember we talked about wavelength over 1 equals speed of sound over the frequency? Okay, you can flip that equation around and say, hey, frequency equals speed of sound over the wavelength. Okay, just so you can say 5 is 10 over 2, or you can say 10 is, what do you call it? You can just flip your formulas around. So wavelength is speed of sound over frequency. Frequency is speed of sound over wavelength. Now, let's do the math. What frequency, what's going to be the resonant frequency of your ear canal? Well, the resonant frequency of your ear canal, the frequency equals speed of sound over the wavelength. It's going to resonate with sound waves that are 4 times the length of the ear. Let's do it in meters first. Then we'll do it in feet. Frequency equals speed of sound, 340, divided by 10. Because your ear canal is 2.5 centimeters long, and it's going to vibrate with sound waves 4 times the length. So what's the frequency of that? Well, frequency is speed of sound over wavelength. Speed of sound, 340, divided by 10. And that's going to be equal to, or I should say, let's see our notes here. Share screen.
34.
Speed of sound over the frequency. Okay, let's see. Speed of sound by, I know what my mistake was. Whenever you do equations, you have to make sure that you're comparing apples to apples and not oranges to oranges. So frequency is equal to 340 meters per second, that's the speed of sound, divided by 0.1, because 10 centimeters is 1/10 of a meter. If we're talking meters on the top, we have to talk meters on the bottom, right? Your numerator has to be the same as the denominator. So for meters is on the top of the fraction, meters has to be on the bottom. So 10 centimeters is 0.1 meter, because there's 100 centimeters in a meter. So 340 divided by 0.1. Do the math. What do you get? Get my calculator here. 340 divided by 0.1 equals 3,400. That's the frequency your ear is going to vibrate. That's high frequency consonants. See? Now let's do it in feet. Speed of frequency equals speed of sound over the wavelength. Okay, what's going to be the wavelength in inches, or in feet, I should say, that your ear is going to resonate with? Well, your ear canal is 1 inch long. So it's going to resonate with sound waves that are 4 inches long. But remember, if we're talking feet, on the top of the equation, 1,130 feet, we also have to convert the inches into feet, because the top and the bottom have to be the same language. So what's 4 inches? 1/3 of a foot, because 3 times 4 is 12. So 1,130 divided by 0.3, whatever. So you do the math. And you'd have to do the math that way. You'd have to do 1,130 feet per second divided by, what is it, 0.3 or whatever. So you do that. 1,130 feet per second divided by 0.3 equals 3,766. Close enough. Well, you're getting close. Okay? So basically, that's the idea. All right? So basically, resonant frequency of your ear canal is going to, because it's a quarter wave resonator, it'll vibrate best with sounds 4 times the length, and whatever that sound, whatever wavelength that is, you calculate it out, well, in feet or in inches, I should say in inches, or in metric using centimeters, and either way you arrive pretty close to the same thing. Because 4 inches isn't quite 1/3, it's 1/3 of a foot, yeah. So at any rate. So, go ahead.
I'm just confused as to where you got the 10 centimeters from. Could you explain that part again?
Yes, your ear canal is 2.5 centimeters long, because 2.5 centimeters are in 1 inch. So your ear canal is 1 inch long. How many centimeters? 2.5.
Okay, and then you times that by 4.
And that's 10 centimeters. And 10 centimeters is 1/10 of a meter. Because 340 meters, you have to compare apples to apples. The top of the fraction has to talk in the same units as the bottom of the fraction.
Okay.
10 centimeters.
I got it now.
Good stuff. You got it.
Thank
All
you.
right. Cool. I like metric better. I'll tell you something, because everything's in tens. And besides, all science uses metric. All hearing aid manufacturers talk metric. So most science, anywhere you go in biology, chemistry, it's metric. So because this is a hearing instrument sciences program, it's best to talk metric. And it's so much easier. 100 is boiling and 0 is freezing. Isn't that just Easy. Instead of 212 and 32, it's like, what? I prefer metric. You'll like it after a while. It's just so much easier. So everything's in tens. Anyway, what else can I lie to you about? Tell you here. Let's see. We are nearing the end of this. Oh, yeah, look at helium speech. Have you ever inhaled a helium balloon? Check this out. Have you ever taken a helium balloon and gone, and then your voice gets really high? How come that happens? Well, it's the quarter wave resonator thing again. Check it out. Your mouth is a cylinder. It's open at this end and it's closed at your voice. So put your hand to your Adam's apple. That's the end of the glass. That's your larynx. And the open end is your mouth. And what's the length of it? The length of that from your lips down through your throat, down to here, is 17 centimeters. So let's do the math. Here it is on your page. We'll just look at your page here because I worked it out. There it is. Helium speech. Why is it high-pitched? Your vocal tract, meaning your mouth, your throat, is 17 centimeters. The speed of sound in air is 340 meters per second. So it's going to resonate best with a sound wave 4 times as long as 17, which is 68. Recall wavelength, frequency, and speed of sound are all interrelated. So frequency equals speed of sound divided by wavelength. So now frequency equals the speed of sound divided by 0.68. Not 68, 0.68, because 68 centimeters is 0.68 meters. And when you divide that, the resonating frequency of your voice is 500 hertz. Okay, cool. But now look at helium. That's in air. The resonating frequency of my voice is 500 hertz, or of my face. The resonating frequency of my vocal tract, my mouth and my throat and my larynx, is 500 hertz. Cool. That's in air. That's regular air as I'm talking to you. But if I inhale helium, and not a joint, I mean helium. Okay, so if I inhale helium, sound goes faster through helium because it's less dense. Helium balloons float, they go up, right? Because air is more dense than helium. So you fill up a balloon with helium, it's going up. So look at the formula here. In helium, sound goes 927 meters per second. So the frequency is going to be, frequency is speed of sound over the wavelength. So it's going to be 927 meters per second divided by 0.68. So guess what? The resonant frequency is now 1300 hertz or higher. That's why helium makes your voice go higher. So now you can actually state scientifically, why does your voice get higher when you breathe helium? As a joke to play. And every time I've gone down to OTC, and when I walk around with Ms. Lynn Royer or Rebecca Krause or any of these people, if there's ever a helium balloon floating around, I always grab it, yank it off the string, and try and undo the knot. And I always do it. It goes nuts. Your voice just goes way up. But now you know scientifically why that is the case. All right, let's finish this with little piece of finale. We got about 5 minutes left, and we're good. The last thing we're covering is this stuff. Impedance. When you think of impedance, it's just resonance flipped upside down. When you take a smile and turn it upside down, it's a frown. An upside down frown is a smile, an upside down smile is a frown. Okay? So when you're looking at the opposite of resonance, you're talking impedance. We said that mass resonates with low frequencies. True. So mass impedes high frequencies, doesn't like them. Stiffness resonates with high frequencies, and stiffness therefore opposes low frequencies. Just like a bouncer doesn't let certain people in the bar. Okay? So it's the same thing. And impedance is affected by mass and stiffness again. It's opposition due to mass and opposition due to stiffness. It's this resonance flipped upside down. That's all it is. So impedance is opposition due to mass, opposition due to stiffness. If you take those two oppositions and put them together, they're called reactants. Reactants. Ariana's getting a headache, and I don't blame her. I'm just about ready to hit myself on the head with a rock, too. Almost. We're just about done. Okay? So reactance is opposition due to stiffness, opposition due to mass, and there's a third element called resistance. And resistance to sound, to the passage of sound in any object, you can think of as simple friction. So in any object, in this cup, its ability to transmit sound or to have sound go through it, the resistance is going to be equal for all frequencies, and its mass is going to oppose certain high frequencies, its stiffness is going to oppose certain low frequencies, and those three working together will cause its resonance. So think of impedance. We'll go to the last page. It's just, keep it simple. It's just the opposite of resonance. Simple resistance is like friction, like ohms in an electric wire. It's independent of frequency. In any particular object, changing the frequency of a sound does not change that object's resistance to the passage of sound. On the other hand, opposition or reactance is due to the mass or stiffness properties. So the opposition due to mass, opposition due to stiffness, those two combined are called reactants. Reactance plus resistance equals impedance. So there you see, resistance equals, impedance equals resistance plus opposition. Opposition due to mass and opposition due to stiffness. So I'll just say opposition due to mass and opposition due to stiffness. There you go. Slain and Pimple. Opposition or reactance to sound, is the opposition to sound passing through is due to the mass or stiffness of it. And in any particular object, the opposition is going to be very different for different frequencies of sound. Anyway, la-di-da. Here, impedance is the opposite of resonance. An object's favorite vibrating frequency is where the least impedance is. Last of all, resonance in any transmission system of sound. Resonance occurs in any transmission of sound system when the opposition due to mass is equal to the opposition due to stiffness. And that is shown in this particular picture at the very end. This is in your textbook, Lass and Woodford. Just have a read of it. Don't freak. We won't be worried about it. I'm not that worried about it. Suffice to say that it's determines resonance. Impedance determines resonance. Okay, next week, we go into the decibel. We go into Unit 2. So be sure to print up your notes from Unit 2 before even joining the Zoom session, okay? Because we're going to be covering the decibel from hell. And the decibel is based on logarithms, but we're not going to sit there working out logarithms. I'd shoot myself if I did. Okay, but you will study why it is on logarithms. Because the range, the softest you can hear compared to the loudest you can tolerate, the loudest you can tolerate has 1,000,000 times the sound pressure as the softest you can just barely hear. So we don't want to sit there dealing in millions. I don't want to say that Samuel's hearing is 627,496 And Ariana's hearing is 406,912. I really don't feel like you dealing with numbers like that. It's way too big. I'd rather deal in 120. 0 decibels, 10, 20, 30, 40, 60, 80, 100, 120. I'd rather do that. It's way easier. So that I can say Ramirez's hearing is like at 60 decibels and Ariana's is at 52. Or I should say 55. It's way easier. So we take a big range and we squeeze it into a smaller range because of logarithms. That's why, but we'll get to that next week. All right, so make sure, unit 2 is the decibel. We'll spend 2 weeks on the decibel. Then we'll spend 2 weeks on complex sounds. And then you're done all the physics acoustics. Then we get into psychoacoustics. Madness. No. All right, so we'll see you when we look at you. Any questions? Do you have any questions so far? Pretty good? Comme ci, comme ça? Not too bad? All right. Mademoiselle Sauvé, hey, Ramirez, and this guy Samuel. See you guys later. The 3 of us, thank you for joining very much. It's always better when people join up. I hate talking into a computer screen myself. You feel like you're insane when you're doing that. So anyway, we'll see you when we look at you. Live long and prosper, and I'll stop recording.